Example 3, ready? For the function below, find each point of discontinuity. This is similar to last night's homework. Yes, no, maybe? Oh, I don't know. Okay.
I think that's like the exact same graph.
Oh, well, let's see. When in doubt, you can totally graph it out. So let's start graphing. When x is 2, right, Addison?
Yes.
Okay. 3 minus 2. You're going to have a hole at where? 1. So there we go. Then it says less than, so I'm going to pick 1. 3 minus 1 is now 2. Then I can also pick 0 to have a nice straight line. 3 minus 0 is going to be 3. Bust out my ruler. There you go. That's my ruler. Then next it says x equals to 2 at 2. What do you do with that piece? Bless you. It's a dot. You're right. There you go. Then over here to the right, I'm going to pick 2 again, and that's going to be an open circle. 2 divided by 2 is again at 1, the same exact location. I'm not going to pick 3, but I can pick 4. 4 divided by 2 is 2. Then 6 divided by 2 is 3. You're right. So I like to pick nice numbers. Okay. Okay. Is that similar to your homework? Yes. So now B says, which of the 4 discontinuities is this one? Okay. Oh, it says which of the discontinued are removable or not removable? Give your reasoning. So out of those 4, which one's this one? It's a whole. It's a removable. Okay. Removable. aka whole. I can take either one. At where? X equals to 2. How do you prove it? Because it says give you your reason. What would you write? The limit, okay? The limit as x approaches 2 of your function equals to what? What is it? It's 1. You're right. Then I have to prove that f at 2 is what? Does not is well, f of 2 exists. F of 2 is what? 2. But okay. But those are not the same. But those are not the same. That's how we prove it. Okay. So properties of continuous functions. You have 5 total. So the first one we are going to start with is I'm going to give you if f of x and g of x are continuous at a point, let's call it x equals to c. Then, here we go. I can add 2 functions. So the first one is the sum. F plus g is continuous at, should be continuous at the same point, whatever that point is. Since we pick c, it should also be continuous at c. So kind of like think about if we pick f of x is x squared and g of x is x to the 3rd. If I add those 2 functions together, would they still be continuous at the same exact location of x if we pick x, let's say 2? Yes or no? Okay, so i.e. f of x is x squared, right? G of x is x to the 3rd. If I add these 2 together, would you agree that I would have x to the 3rd plus x squared? Okay, I'm going to pick a random c location, like 2. It's f continuous at 2. Is g continuous at 2? Now, if we add those 2 functions together, is this right here continuous at 2? Yeah, so that's really what that means, okay? Same thing with difference, same concept. The difference, okay? If you do f minus g or even g minus f, okay, it's still continuous at your chosen value of x. which is our case C. What if you multiply your two functions? Guess what? If it's continuous independently, it should still be continuous. Now, oh, different. Sorry, I forgot a T. Okay.
So when you're writing like f,
sorry, that's not a different. It's difference. Subtraction. Okay.
When you're writing f minus g or g minus f or the something,
Mm-hmm.
are you meaning f of x minus
Correct.
g of x?
Correct. F of x minus g of x. Okay, like that. Or g of x minus f of x, like that. The two functions subtracting one another. Sorry, that is a difference, not different. 3, we are going to have the product. Same thing. If I multiply the two functions, f and g, okay, so f times g is continuous, okay, at x equals c as well. Quotient, it's almost 100% true except the denominator, except when the denominator is not what? 0, right? Okay, so the quotient, you can do f divided by g is continuous at the same value of c that we have picked, except g of x can never ever be 0. It's also true if you were to multiply by a constant. Okay, so constant, if we take k times f of x, which is your function, or even k times g of x, guess what? It's also continuous at x equals to c. Okay. Now, who remembers composition of functions? Okay. Chanel, can you remind us what those were? Composition.
Like f of g of x.
That's right. Okay. So composition is a little bit more difficult to kind of think about it. So let's review that really quickly. If I said f of x, oh yeah, let's use earlier x squared, I think. And then let's say g of x equals x to the third. Okay. Can someone tell me what would I need to do if I want to find f of g of x of, let's say, 2? How would you compute that? What do you do first? Trey?
Do you plug in the function of g into x? I mean, into the function of f, or f of x?
Do you guys remember that?
And then you plug in the 2 for x.
Right. First, you take the 2 and you plug into which one? The g. So g of 2 is what? 8. Then that output is the new input. Remember this? And then now that gets f of 8. And that's going to be 64. So the composition of 2 is 64. Okay. So this one is not the same as the last 5 properties. It's a little bit more difficult to. So if f is continuous at x equals to c and g is continuous at f of c, okay? So this is where it's slightly different. Can you see that this is saying that, okay, well, if my c is 2, right? Then we're saying, okay, if g is continuous at 2, but f has to be continuous at g of 2. So that's what that's saying. Does that make sense so far? Okay. This is composition, okay? Then the composition of g of f, which by definition, by the way, is g parentheses f of c, okay? So g bubble f equals g of f of c is continuous at x equals to c, okay? Meaning the limit as x approaches c of g of f of c is equal to g of f of c. Okay. So if it's continuous, it has to exist, right? Okay. All right. Last time when you were doing your homework, was anything asking about the extended function? Any question that has? No? Okay, good.
So when we're doing the continuous function thing,
Uh-huh.
like g of f of g of 2 or whatever,
Uh-huh.
are we allowed to, let's say you just wrote, you just put in the function of g into f first, and then you,
So
it was
take
like x
this,
to it was like x to the 6th, and then you plugged in your x value. Would that be right?
Where am I at? So it's
So-
over here, right?
Yeah. So
Okay.
if you do your algebra first before plugging in, so you
This right here is the same as this definition. I mean this one right here. Is that what you mean?
No.
So,
Yeah.
but this one I did g of f. In our example, I did f of g. So the variables are the functions are reversed.
Yeah, I was just asking if you did the algebra first before you plug in your variable. Is that
Like
the same
what?
thing?
What would you do?
So if you do f of g, that's
Like take this and compose into that.
yeah.
So
would
that's
be,
gonna be x to the 6th.
yeah, and then you plug in your variable.
And then 2 to the 6th, of course.
Okay.
Yep.
That's the same.
It's just sometimes with variables, it's a lot more difficult to compute the power. Or if you get the power wrong, the whole thing's wrong.
Yeah.
Yes, that would totally work. Okay.
All right. So this one's really about the language. Okay. Give a formula for the extended function. So this is, I want to talk about this. It sounds scary, right? Extended function 4. Here we go. F of x equals x to the 3rd minus 1 all over x squared minus 1. That is continuous at 1. So in plain English, I want you to give me an equivalent function that is now continuous at 1. So it's f of x currently continuous at 1. No, because if I plug 1 in, what happens? Yeah, 0 divided by 0. No bueno. Okay. So when you see something like this, this is the simpler of the two cases. I just have to factor. Who remembers how to factor the difference of two cubes? The first one is x minus 1. What's the next one? X squared. What's next? Oh my. Not minus. Plus. X plus 1. All right, let me give it to you. A cubed minus B cubed. Someone give me the formula. It's always A minus B times the quantity over A squared plus A times B plus B squared. Okay. Same thing as if I were to have a sum of two cubes. That was the difference. So this is A plus B times A squared. What's the difference between those two formulas? Now is A minus AB plus B squared. Okay. Anybody remember SOAP? Yeah. What is it, Anthony? Right. Okay. Now on the bottom, it's going to be an x minus 1 times what? What's the other factor for the denominator? Go ahead. Can I reduce? Yes. So let's reduce. So now we have x squared plus x plus 1 equals x plus 1. Okay. Now look at it. What happened if I plug 1 in now? Is it okay? Yeah, I'm good. So that is a new function that's going to be continuous at 1. So it looks scary, but it isn't. Okay. Last one of the day. I think you had something like this last night, yeah? Or maybe not as scary? Or maybe not as easy? Sketch a possible graph for this function. Are you ready? Okay. Let's recap really quickly. If it says it's a function, what line must your graph pass this? Yes. So don't make sure you when you graph it out, check the vertical line test to see it passes. Okay. Restriction number 1: f of -2 must exist. What does that even mean? It has to be continuous. Is that okay? Yeah. Number 2, next restriction. The limit as x approaches -2 from the right of the function is the same exact value as f of -2. Now, so tell me, how do we do that? What do we do? The limit coming from the right side towards -2 is the same as its algebraic value. What do you want to do? Next piece, the limit as x approaches -2 does not exist. We can do a lot. There's an infinite many different answers. Okay. Yeah, okay. Let's talk about -2 coming from the right. Would you agree? Because at f at -2 has to exist. I can put a hole anywhere, right? Top, bottom. Would you agree? As long as you pick a location. So let's say I pick it right there. Does it matter the y value at all? No, it didn't say. So I can pick any y value I want. So right now, did we take care of that piece? F of -2 exists. Yeah, we have a closed dot. Check. Then it says, hey, the limit at x approaches -2 coming from the right is the same thing. So whatever is happening, can I go like that? Yes or no? I mean, you can look pretty. You can go, yeah, you know? You can go, yeah. I mean, you can have so many different choices, okay? Now, it said, well, but the limit at x approaches -2 does not exist. I mean, the left and the right cannot be the same. So I can go somewhere and do something else, right? Is that okay to have that curve on the left side? Okay. Yes or no? Yeah, I can have a straight line, right? I can have, if I don't feel like drawing curve, I can have this, couldn't I? Oh, so pretty. All right, you can have infinitely. Now, check them. Is it a function? Yeah, for sure. And that's it. The end.